Okay, we are very honored today. It will be the last lecture of Professor Gordana Todorov, and she's finishing today this extremely illuminating series of lectures. Thank you.
Thank you. Okay, so let's see. Okay, last lecture I finished with Auslander algebras, and I want to go. I'm just going to recall Auslander algebras, the entire Auslander algebras. So Auslander algebra gamma means that it is algebra such that the global dimension of gamma is less than or equal to 2, actually usually is equal to 2, and the double dimension gamma usually 2, when you have in this semi-simple case, then they're not equal, otherwise it's always 2. So it was the theorem of
Don't we need also gamma to be what is Hardinian or this of one?
oh, this is it's Artin algebra. Yeah, I should say. So I think anything you don't know about is Artin algebras or something, sometimes finite dimensional algebras. Okay. Is that there exists bijection between algebras lambda. Again, everything is Artin algebras lambda, which are representation finite. Okay. Well, we can now say Auslander algebras. Of course, he didn't say Auslander algebras, but we're just going to say Auslander algebras since it is fine here. And everything is up to isomorphisms and up to Morita equivalence. So it is really okay. So now, so the idea was here. So this is just the idea of proof, because it is representation finite over n, which is n pi plus n. And then you take the endomorphism algebra over lambda of n, and that is gamma. So gamma is defined to be this endomorphism of n over lambda. And if you start with, and then one proves that this has actually last time I proved that it has dominant dimension less than or equal to 2. And I just stated it that it has global dimension less than or equal to 2 because it's abelian and you have current mode and that gives global dimension less than or equal. But then, so that is correspondence in this way. But then if you start with gamma, then if you take Q to be direct sum of QI's I1 to n, where QI are projective, injective gamma modules. Then we define lambda to be the endomorphism of Q over gamma. And that will be algebra. Then the theorem said that that will be algebra, which will be representation finite. So this is this correspondence for Auslander correspondence. Then Osamu Yama defined higher Auslander algebras and gamma to be the algebra such a global dimension of gamma is less than I call now. Usually puts here as +1, but I mean it's as dominant dimension of gamma. So it's the same idea that global and dominant dimensions are values. Maybe it was for Auslander algebra. And then again, gamma theory. Says that there exists bijection. And here are higher Auslander algebras. Algebras. And now here, okay, and now here it cannot be algebra's representation finite, but it will be something which will have some finiteness condition. So it will be pairs. Lambda and C, where C is cluster tilting subcategories. And then the condition here is that it is finite. Okay. So here we have Auslander algebra is homological condition, right, on global and dominant dimension, and it is related to finiteness condition here. Now here, Young's theorem is again homological condition on gamma. Higher Auslander algebras are called gamma. Again, it's higher, it's again homological condition, and it is related to certain finiteness. It's not that lambda is a representation of finite, so, but it is certain finiteness of certain subcategories.
And C is a subcategory of mod lambda?
Yeah, I'm just going to write it.
Oh, okay.
Yeah, because
Just
I
to
will
understand
see
better.
cluster till be a subcategory. I should say subcategory of
Yeah, okay.
mod lambda. I
Yeah.
was going to write in the
Yeah, no
definition.
need.
And finite means it has finite immediate comments. Right?
Yeah, finite and indecomposable,
Indecomposable.
non-isomorphic.
Just not check it.
Yeah, in mod lambda. Okay, so I want now to define what is this cluster tilting subcategory of lambda. So if global dimension lambda is let's say S. Just see because I want to use the same. So if global dimension of lambda is K, then K plus the tilting subcategory of lambda is C. Consists of all objects X in lambda such that X I of X and C. Oh, C. Okay, let me just leave C at this point. Just C because I didn't put any C case. Such that X that this is equal to 0 for I between 1 and A minus 1. And it is the same as the condition X I C X is 0 to the same condition. So it's essentially maximum subcategory, which doesn't have any extensions up to K-1. So, okay, so I will erase this because I wanted to write something else. Okay. Except that is not the rule for one board talks, if I want to prove two board talk. Okay, so the correspondence here is again the thing n to be n1 plus n. But now this is from this cluster building subcategory which has 5 objects. Right, so I'm not taking all objects in one lambda, I'm only taking objects in this finite cluster building subcategory. Okay. And then I think that then gamma is defined to be the endomorphism algebra of n over lambda. So it's exactly the same way that gamma is defined. And if you have gamma, then again you take Q to be the sum of the projective injectives. And you define lambda to be the endomorphism algebra of Q, but now with gamma. So that's exactly the same construction. The only thing is that here we also need this cluster tilde, because here we have to have the whole pair. So we get lambda, and you also need to this have a finite cluster tilde sub. Okay, and that pair is what is started. And there is a lot, so here's the cluster tilde category, and there is a lot of study about these cluster tilde subcategories. I'm not going to expand on that, but sometimes you could have your lambda of global dimension k, but sometimes you have actually cluster tilting subcategories, not with k, but with half of the k or something like this. So there is, I would just say there is a lot of study. But that will slow me down to what I want to finish today. Okay? But I just want to point out that there is a lot of study on this, this cluster building subcategories. So, what I was I was saying, well, I would just like to see more higher algebras. That was kind of like a basic approach. You know, we know all these Auslander algebras, so how to find more Auslander algebras. So that this was the idea. So, is this okay to find something?
And I missed this, the original picture corresponds to what value of k?
What?
The original picture corresponds to what value of k? That one, yes.
Corresponds to k is equal to 1, right? Right? Like this,
Yes.
so k is equal to 1. I think that's why this is defined global dimension as +1, so that it corresponds to s is equal to 1.
And what's the relationship between s and k?
I guess that's why I was going to write.
Okay. It's
No, I have to be careful because see, this can be S Auslander, higher Auslander algebra, but this will not always be just S or S minus 1.
Okay.
It will be, there is a different thing.
Okay.
Actually, if algebra is of finite representation type, this will always have global dimension 2.
Yes.
But this lambda can have global dimension 8.
yes.
Okay, so there is no relation between global dimension and global dimension here. So that's why when I was talking here about K cluster building
Yes.
subcategory, I didn't want to use the same as. That's why I wrote that, and then I said, no, that's
Yes.
difficult.
Yes.
So you're saying that this bijection in the higher case cannot divide them based on the S, but it's all higher Auslander algebra, but it's all pair, right?
Yeah, so that there is this correspondence that is a pairs, yeah. Okay, so now I want to define some higher cluster algebras. And I want to do that at this point. Oh, yeah, okay. I didn't divide my board correctly, so it doesn't match what I was. Okay, so the idea is just to find more alpha. Find more higher. Okay, so in order to do that, so and then construct it like the whole families of these, we're very happy. So so it's not that we'll describe all of them, but it will be like large families of higher algebras. But then, again, we start with Q, but for these constructions now, Q has to be division. And H is KQ, so this is the factor. And DB H is the derived category of bounded complexes. Because last night I didn't say what this B stands for, so it's kind of the bounded complexes. So that is what we already talked about. And then after that, I defined a cluster category. So cluster category is this side that is, I have no trouble. And here I seem to have trouble. Okay, let me just move this side. Okay. So C is defined to be dB, but tau minus 1, shifted 1. So that was cluster category. And then we also defined F to be the fundamental domain of C, and then F consisted of all the modules mod H and union the shifts per shift of H, and then we take full subcategory of the derived category. So this collection of objects here, we're going to look at them. They're in the derived category. They are in this full subcategory, and they're also up in the cluster category. So we're going. I'll come back to this again. But then we also define CK to be the derived category, and tau minus 1 K. So this is K cluster category. And now again here I have to say this K is not fixed. Sometimes this is called K cluster category, sometimes it's K minus 1. We are trying now in the paper with Osamo, we are changing certain, so this plus minus 1 in many situations is, you have to really be careful whatever you are reading to decide which K you are using. Okay? So this, you see sometimes this orbit category is denoted here by CK K plus one or CK minus one or something like that. It's just question of notation. I mean, the definitions are still the same. It's just question of notation, which index you put here. Okay. But this is kind of originally the way it was done. Okay. And then you have FK to be fundamental domain. And of CQ. And now this FK is actually from subcategory of the derived category consisting now of union of mod H shifted H, where H goes from 0 to K minus 1. So this is like K0, right? And union H shifted K. So this is just for K is equal 1. Right? If K is equal 1, then this F is just mod H. Yeah, you just get mod H, not shifted, which is actual mod H. And here you put H1. Okay. And then okay, then one more thing that I want to denote here is FK. So now this is supposed to be object. This little thing is the category, but FK is the object, which is equal to. Now, if we take all in the composable modules, you see this family that I use here for algebra representation finite. Since here in the thinking case, that's also algebra representation finite, right? So I'm taking M to stand for all in the composable modules, okay? So I'm going to take FK, so from mod H, I'm going to take M, meaning sum of all in the composable modules. But then, because I'm taking here shifts J. J goes from 0 to K minus 1 and plus H should be K. So now this is an object, right? This was a category and this is an object. And now let me just remind you how the derived category was. Again, I'm using the fact that H is here, because otherwise derived categories will look differently. So the derived category, we're going to draw it now, let's say. And I'm going to take, okay, so the part where the projectives are actually has the same shape as the quiver, okay? So sometimes it's straight line, sometimes it's DL, sometimes this. So this part here stands for all the projectives in the AR quiver, right? We pointed out that AR quiver always starts with projectives. Okay. And then it will end with injectives. So it will, so the AR quiver, this will be mod H. This will be exactly projectives H of this is projectives. This is injectives because the AR quiver of just mod H starts with projectives and ends with injectives. And then the derived category will have here shifted projectives. So this is H shifted. And then it will go again up to shifted injectives. And then H double shifted. And it goes up to injectives. But each of these pieces looks exactly like mod H and it's only shifted. But because it's hereditary, it was not hereditary, but because it's hereditary, they look all exactly the same. And then because it goes down, down, down. And then this is mod H K minus 1. And then this is mod H shifted K. And this part here is H shifted K. Okay, so it's just the way, right? I think it's, I mean, that, you know, I drew it several times on examples, so this is exactly how it looks. Okay. So I just want to point out that this fundamental domain of K cluster category goes all the way up to here. Doesn't include this, but it is all the way up to here. And we'll use that later, so this picture will be used. Okay. Now I want to state the address theory. Okay. So now let H be KQ, and Q is thinking. And let F K be the additive generator. Okay, I'm just going to write in words that, you know, Fk is additive generator of the fundamental domain of Ck, but I just feel like here it should be stated properly. So let Fk be the additive generator of the fundamental domain. Of the K plus the category. C, K. Okay, so I'm just defining, the point is I'm looking at H and I'm looking at that, right? Okay, so now I'm going to make the statement. So now with this, right, so there are several parts. The first part is let gamma K be equal and the morphism algebra of Fk over dB. So this gamma K is now take all the objects here, 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 and including these, okay? That is what it says. So Fk are all the objects up to that point. And then gamma K is the endomorphism algebra of that object. So it is kind of just like Auslander algebra high. And then gamma K is Kairos algebra. Algebra and global dimension of gamma K is less than or equal, actually equal to 3K plus 2, and it is equal to the dominant dimension of gamma K. So you can see that if k is 0, right, I was pointing out that if k is 0, then if k is, okay, go again, off. This is supposed to be if k is equal to 0. But yeah, here I'm doing endomorphism. Yeah. If k is equal to 1.
Mhm.
Is equal to 0. Then,
You just have the modules of recovery, right? That's correct.
No,
That's
because the formula goes to k minus 1 up there. The problem comes with the k minus 1 index up there. You can't really have k 0. Unless the index goes to k here.
okay,
Mhm.
actually,
Mhm.
okay, so the thing is that, okay, so if k is equal to. I mean, we have two versions of the way it's written, okay, so once it's written, this is what I was saying, you know, is it k or k minus 1, okay? If k is equal to 1,
Mhm.
okay, then, so here I was talking about k being equal to 1, right? Because I'm taking h1, so I'm talking about k is equal 1. If k is equal to 1, that means I'm taking only mod h and this. Okay,
Yes.
and global dimension. Then this should be global dimension of gamma. I thought I fixed these pluses and minuses. This is about, okay, well, let me just leave it like that because of this plus minus. Okay, so the point is that this is supposed to be, if k is equal to 0, this is supposed to give me exactly Auslander algebra.
Okay.
Right?
Which is true, because in Auslander algebra, I'm not taking H1. I'm taking just the module category set.
Yeah.
That coincides exactly. You're right.
Right. Yes, sure.
Over there, we are not thinking k is equal to 0, but because we are thinking about.
Yeah, here, what I
Yeah.
mean is J goes to. Yeah. I think now it is.
Yes,
Okay.
I think now it's,
I think it is now, okay.
I think
So-
it should be from 0 to
Zero.
Equal 0, I don't get,
you can put 0, mod H0 is the module category itself. H0, but there's no H0, maybe. Yeah, that's, I think we can just leave this formula for K plus category to be.
that's why there was this issue of what to think, you know. Okay, so
one way.
so let me just write exactly what this is supposed to be. Okay, so here when I'm writing this, okay, I do want to go with fk. If I think, okay, here is k0, k1, and I go over it. Okay, and I take endomorphism of all of these.
Mhm.
And I take endomorphism of all of these. The global dimension will be. So I'm taking endomorphism of all the modules, including. Maybe I should, yeah, that's not what I wanted. I didn't want to. I'm sorry, yeah. That's why there's a confusion, okay? I want, okay, so I don't want. In this theorem, okay, there are two parts of the theorem. In part B, I will be talking about this, okay? In part A, I want to take sum of all M shifted J, where J goes from 0 to K. Okay, this is what I want to take. And I want to take endomorphism of that M J goes from 0 to K. Okay, let me say exactly what it is for. So M is the sum of all the intercomposable modules here. So M is sum of all of those. Okay. This is M shifted, and this is up to MK shift. Okay. So gamma K, so I'm not talking in, this will come in the second part here. Okay. I should have not written at that point, I should read that. Okay, so I'm taking endomorphism of everything up to here. Okay, and then that is gamma K, and then gamma K is higher Auslander algebra, and global dimension of gamma K is 3K plus 2, and if K is equal to 0, that means I'm only taking M, and endomorphism of M is just Auslander algebra, and global Auslander algebra is 2. Okay, is that okay now? I'm sorry, but
No, it's good.
confused. So that was the part A. Okay, now I will talk about part B. Okay, and the reason, so, okay, so see, once you have higher Auslander algebra, okay, then you also want to see what is this algebra lambda here. Okay, and to see this algebra lambda, you want to look at your higher Auslander algebra, which will be that algebra, and take the projective injectives and take endomorphism of those. And that will be the new lambda of. So part B now is, or maybe I should call it I guess, but it is according to this theorem. Okay, so let's lambda be endomorphism algebra of Q i's over gamma K, where Q I are projective, injective gamma K modules. So this theorem was, okay, let's construct higher Auslander algebras and let's see the Osamu's theorem on that, okay? But then after he wrote this, then there was this nice part, and this is the part which will connect now to the preprojective algebras, okay? The nice part was that this lambda, when you take this endomorphism algebra of the projective injectives, this algebra lambda is now isomorphic to the and K. This okay. So what happened is, okay, there is higher Auslander algebra, then there is Osamu's Iyamas theorem, which says to find this lambda, but then what interesting thing that happened is that when Emre looked at this lambda, he showed that this lambda is exactly endomorphism algebra of the fundamental domain of the higher cluster category. Okay, so we have higher Auslander algebra and fundamental domain of higher cluster category. So that is this theorem. And now I want to talk, so now this FK was kind of the thing that we continued working on. So at first area, and then after that we did it on factors. Okay, so now I want to talk more. So this FK is the important. So let me just again repeat what is FK. So FK are all the objects which go from here up to here. So FK it goes up to FK minus one and only HK. Okay, only projectives at the next. Okay, it's just the same way that we have fundamental domain for the ordinary plastic. Okay, so now the next of the board will be everything about FK.
So just before you finish, is this is specific for thinking type or
This
there
is
is
for
an
thinking-
extension
no,
of this theorem to pertain?
This is for thinking type because we need M to be a module. Okay?
Yeah.
And that will be the first half of this board will be about that.
Okay.
And then we
Mhm.
expand it to non-thinking type
Mhm.
by expanding instead of projective modules, we
Mhm.
will have projective functors. So we'll use very much what I did at the end of last lecture.
Okay.
You know, at the end of last lecture, I
Mhm.
described, when I described, maybe I can even say here. See, so projective functors. So I describe projective functors, you take a point and you take harm into this. And then you get, and that is harmed by the head.
Mhm.
And then if you go all the way to injective and you take then you end up from projective to injective.
Mhm.
Okay. Now, the beautiful thing, okay, so I'll go further. So this is, when you look at the modules and then this category is representation type. If this category is infinite representation, the functors still behave the same way. So you can use all the argument that you use here for these projective modules, which is true from projective functors.
Mm.
And furthermore, you see this projective functor here, if I take projective functor here, it will look just like this one. So all the tau of different things will have the same structure. You know, it's not that they'll be supported on the same modules, but they will have the same structure. So in particular, I said here that harm into injective. Right? That this is projective injective. Oh, well, if I put that, okay, that is projective injective module over Auslander. Right, that's what I said yesterday.
Mhm.
But then, if that corresponds to this one. But then if I take tau, I can take but now in the derived category of some tau minus t of any module. Then it will be here and it will still be projected exactly like that. Okay. And so that was the nice thing about that. And we can keep going and we get a lot of projective injectives. Okay. And that's why endomorphism algebra of these projective injectives will end up like this. Okay, so that was the reason that this theorem was true. Okay. So the point is the only ones that are not projective injective are from here, but then when you're on the left side from objectives, that they're projective, but they're not injective. Okay. So let me leave this and I'll probably come back to this picture, but let me first make statements. Okay, so now I want to look at this. Okay, so for now I'm using data. so that I can talk about modules, endomorphism algebras, and so on. Okay, then after about here or second half of the board, then I will switch to non-thinking, and I'm just going to take project instead of projective algebra, projective algebra. Now for this thinking curve, I'm going back to FK. So now FK is this fundamental domain of the K cluster category. And I'm going to, if you want to, since you're taking picture here, I just moved the board so that you can get the whole board. Thank you. That's what I asked you yesterday to do for me, so. Okay, so I'm going to take FK to be the sum of M J. J goes from 0 to K minus 1 and plus HK. So it's exactly the fundamental domain of the cluster category C. CK is the cluster category CK. Okay. So now the three things. FK is an object in DB, right? Because clearly it's an object in DB. Now FK is an object in FK, because you see FK, when I define FK, FK is the full subcategory of DP consisting, getting from these objects. Okay, so it just FK is an object of that category. Okay. But then also FK is an object of CK, of the cluster category. So now I can look at this FK in three different ways. Okay. Now, if I take endomorphism algebra of FK over DB, and I look at the endomorphism algebra of FK in the category FK, this will be the same because FK is full subcategory. Is full subcategory. But if I want to look at FK in the cluster category, CK, here they're not equal, and this is where we need preprojective algebra. Okay, so here we need preprojective algebra to make this statement, preprojective algebra. So that's kind of approach, and yeah, okay. Where's the window sometime?
Lots of time. We started very late.
Okay. Okay, so now let me talk about preprojective algebra. So typically, you start with Q, so the original things about preprojective algebras, you start with Q, which is equivalent to 0 Q. Okay. Now there are three different but equivalent definitions of a preprojective algebra. Okay. So the first one which we usually see is clear definition. So you define Q bar, Q0 bar, and Q1 bar. So Q Zero bar is the same as Q0, meaning we keep the same vertices. And Q1 bar is Q1 union Q1 star, usually denoted by star. So typically, if you have arrows like that, alpha beta, then you add alpha star here and beta star here. And then you also put relations. So the preprojective algebra is defined, preprojective algebra of Q is defined as the path algebra of this Q bar, this Q bar, mod relations, and then relations. I'm not going to use them, but let me just write them quickly for this. For this relation is alpha star, alpha star, alpha star alpha, or alpha star plus beta star beta, and the other one is beta star. Okay, so for any point in the middle, you go in and out, and sometimes you do it with plus. There are several definitions. Bill Croyboy has different definitions and different statements about his preprojective algebra. So sometimes with plus minus, or you can do other things. But I'm not going actually to deal with this, so I'm not going to talk about this now. The second definition is you look at the X1 of VH. These are all injectives with H. This is a nice bi-module, HH bi-module, and you create the tensor algebra of that, and that is the preprojective algebra of Q. So that is a different definition of that. Okay. So notice that this X1 DHH, so that means it's all the extensions with the DHH. This is DH, this is H, so it's all extensions of these by these. So that's where you have your X1, right? And then the third one is you think H plus tau minus of H plus tau minus 2 of H plus until it stops. But it will stop because we are talking here about finite dimensional. So that will be one way of defining. So what this is actually, you take H, then tau minus of H are all of these, and tau minus 2 are all of these. So what it says, take these modules, take all of them up to here. And that there is a particular way of defining how you multiply. Okay, it's not completely trivial, but yeah, you shift them and then you multiply, you compose essentially that. Okay? But the point is that using preprojective algebra is a direct sum of these are H modules. Now this is preprojective algebra. So it is actually sum of projective PQ modules, right? Because every algebra is sum of its projectives, indecomposable projective. Okay? So this here, when it's written like that, see this right side is, I'm in the wrong place. This right side is sum of the H modules. And we need to say how you multiply them, which I'm not saying, but one can define it precisely. And then it gives you modules, it gives you preprojective algebra, but preprojective algebra is sum of its own projective modules. So this is kind of preprojective algebra modules, and this is H modules. Okay, and this is how higher preprojective algebra will work. And this is how higher preprojective categories will work. So that's why I'm emphasizing so much here, because this is, yeah, and then people prove that these are equivalent statements, Riegel proved some, and I mean, different people prove different parts. Helmut Lansing did and so on. Okay, then we have higher. I decided to put higher on the left side, on the right side. No, I decided to put it here. And now I want to talk about the higher preprojective algebras. And that is P gamma and optimal. So they define for lambda global dimension. Lambda is this. So lambda is a finite global dimension. Is it okay if I talk a little about it?
Of course, no,
Okay.
of course.
Okay, so lambda is of global dimension. Yes. Okay.
When people start jumping out of the window.
So we define preprojective algebra of lambda. This will be higher preprojective algebra. Now, because you have global dimension S, you look at X S of lambda. So again, higher X of injective projectives. It is a nice bi-module. And we take a tensor algebra. And then this is the definition of the preprojective algebra of algebra which has global dimension S. And actually it is high preprojective algebra, and I believe they put here S plus 1. Okay. So this is the high preprojective. And they also, so that is the definition. And they also have the theorem which says that this higher preprojective algebra of lambda is equal to, or isomorphic to lambda plus L minus S lambda plus like that, or B lambda plus L minus tau plus S lambda plus like that, but tau minus S is tau S, sorry, tau S is called higher Auslander method. Higher Auslander right hand translation. And it is actually defined as omega S and then composed with tau, or this is tau minus. You have to shift. So instead of taking, see, almost consequences, right? Take your tau from here to here, but now first you do certain syzygy and then do tau of these syzygies. And now I'm not sure exactly what it. Yeah.
Can you use the tau functor to define something like pre-injective algebras? Should be in the
Pre-injective. I think in many, I guess you could, but I mean, this is not even exactly how in general. So yeah, probably if you define probably in many situations it would be isomorphic. That's my guess, but I don't know. Okay. Okay, so this is now higher preprojective object. Okay, so now we are interested in the endomorphism algebra of Fk over dp and endomorphism algebra of Fk over Ck. Right, so we are interested in these two. And they'll be related with preprojective algebra. And we know that this one, when we compute this over dp, then we know, oops, I didn't write it. Global, that is also part of this theorem, the global dimension of this lambda here is Gk plus one, so it's only one down. In general, it doesn't mean that, when you take this lambda, see that when you have Yama's theorem, gamma and lambda can have different global dimensions. But this particular gammas and lambdas, we have the correspondence is just one going down, just one. Okay, so that means now, and then here's the theorem. So this is theorem. Again, that is animation. So you start, so this is still for Q thinking. And Fk, again, this fundamental domain. Of Ck. Then endomorphism algebra of Fk when viewed as objects in Ck, so it's this one, is actually isomorphic to the preprojective algebra of the n of the same entity, but now over the derived category. And because we know that the global dimension is 3k plus 1, then it is 3k plus 1 preprojective algebra. Or because I said that this dp and Fk are the same, then you can also say this way. Preprojective algebra of 3k plus 1 and of Fk and over Fk. Now, I wanted just to indicate was the idea of the proof and then how that goes to in general. Okay. So the idea of the proof is this algebra, right? Because here, notice here I define the higher preprojective algebras, right? So I define higher preprojective algebra of lambda. Okay, so if throughout the description this will be like lambda. Okay, and then I want to look at the higher preprojective of that. Okay, so what it says here is that the preprojective algebra is sum of lambda plus tau shifts of lambda. That is higher tau shifts of lambda, or then d lambda and again higher also derived shifts of lambda. But when you look at the algebra is sum of its projectives. That's what I keep repeating. So what you can do to do this, you see, it will be straightforward proving this. Okay? So to prove that, you look at the projective factor here and show that it is direct sum of the tau orbits of projective vector here. So it will be exactly using this. So, let me, so here's the idea of proof. So I want to look at the projective, module, later it will be projective module over and CK FK, right? Because this is one that I want to show that is equal to the preprojective. Okay, now projective module here is from CK into XI from FK, right? That is what I was kind of emphasizing when you take endomorphism algebra of something, it is the projectives are part of that something into indecomposable summits, or not necessarily decomposable. So this is projective module. So now I'm trying to describe projective modules here. Okay, and then I'm trying to get to there's a short exact sequence. Okay, and here is HOM over FK of FK to the same XI. Now, this is a projective module over N FK. Okay, so this is projective over N FK FK. Then the exact sequence had here D from some other X prime, which is described precisely. No, it's X, yeah, some other X prime into FK. Now, last time I talked that injective objects, the projectives are blank somethings, and injectives are duals of something's blank. So this is something blank, right? We can do because I'm computing of every FK. So this is actually injective. So this is injective over and FK. FK. So now, and this is exact. So now I'm just going back to that. Projective over the preprojective algebra is sum of the projective and shifts of the projectives. Okay. Now, there is this statement and one more statement, and that is that this D bound that was part of the proof. This is how over FK. XK. FK is actually isomorphic to tau 3K plus 1 of the FK on the left side. XI. Okay. So now you know that this is projective module over this is equal to, so this projective module CK FK XI is isomorphic to a projective plus tau, well, it's tau minus, sorry, 3K plus 1 of the projective, and it already reached injective. So now going back to this, it says that this algebra here, the projectives, or this algebra, if you just add them all, this algebra is sum of projective and shift of the projective. The only thing is that in this case, that this shift is short. You reach injected. You see, in general, you may have to go for longer tau minus, tau minus, tau minus, okay? But in this setup, actually, this injective already happens to be tau minus 3k plus this. So we got that the harm over this is equal to the projective over this, right? So if I'm thinking about this lambda, then this is like lambda, and this is like tau minus of lambda. So if I add all of them, right, then I'm getting this. Okay. So then that says that this is pre-projective algebra of it is 3k plus 2, because for pre-projective you have to add 3k plus 2 pre-projective up here, and I made a mistake here, I should have put 2, sorry. Of the endomorphism of fk over fk. So you look at the same collection of modules or objects. If you look at all the objects up to here, and you look at the endomorphism algebra. If you look at those objects just within the derived category, you get certain endomorphism algebra. If you take these objects and put them in the cluster category, and cluster categories orbit categories, so it closes, so you end up with more morphisms going from here back to the beginning, then you end up with getting pre-projective algebra.
Yeah, sorry, I mean, is X prime the left approximation defined yesterday, or? The proof in the short exact sequence here, in the end term, if there is there is an X prime.
Okay, it must be, because it is actually this factor restricted to fk. You see, it's blank xi. Here it is within ck, and here is the same blank xi restricted to fk, and that is approximation by blank fk's. Yeah, you're right.
So is X prime the left approximation?
No, this x prime, it has, it's not the same xi, but it is closely related. It's tau of xi or tau minus, so it's closely related, and I didn't remember actually this graph. Okay, but it is closely related to that. So that one can do this part. Okay, and now I just want you to say, do I have now time for cluster switches? Yeah. So I just want to kind of make a few remarks. Okay, so the first, I guess the first remark is that if you have an additive category, okay, so actually, what you need to have pseudokernels, okay. Then you have your meta lemma, which says that the category is equivalent to the all so essentially that to look at the category, you can look at the projective factors which are defined by that category. Okay, so that's essentially your method. And then So anyway, let me go back to this. Okay, so that, so, yeah, so it's, so now I'm going back, I will have to look at the, yeah, I know now. Okay, so that means I can look at the category FK using that as it is equivalent to the category of harm FK into XIs, where XIs are in FK. And this is straightforward. And I can, now FK are also objects of CK. And we have the whole CK, so I can also look at, I try to write it so that it's as precise as. Okay, so that's good. Yeah, okay, now let me write the other statement. And do it, okay. So so that was my first statement. Now the second statement was that FK over FK is this is just the definition, right? This is the sum of harm over FK of FK into X i's, okay, where X i's are elements of FK. Okay? I mean, this is nothing, just the endomorphism is some of the terms. And then, okay, so here is now what I want to do. Okay, so let me write first theorem the way the analysis is stated. And then I'm going to use these two facts to go from this to this theorem, but now just using factors. Okay, so the theorem is that, and so this is the theorem. Is that the cluster category CK is, I think, moving to the pre-projective DK plus 2 category of FK, where FK was the fundamental domain. Okay, so now this is purely in terms of categories. Okay, so now let me just say how, explain that. Okay, so first of all, CK replace by by the collection of all harm over CK of blank XI's, where XI's are in CK, okay, or representatives of CK. But you see that we are taking our FK to be all representatives of everything in CK. So this is just replace CK by this. Okay. Now the other part is that replace. Okay, so instead of writing with that, we can say replace by category generated by this. Okay. And now when you have this category, now you do your mega. We're doing two separate things. I try to do faster, but let me just do exactly in the order that I wrote. I think it doesn't make sense to try faster myself. Okay. So, okay, so what I'm doing, here's my FJ. Okay. And. I'm not going to skip, I'm just going to. So I want to move it and. J. And J. And I want to replace it. Now, if it is not finite, I'm going to replace, so you see, N and K is some projectives, okay? So I'm just going to replace my subcategory of and J like XI, the XI are in FK. So this is kind of very straightforward, right? Endomorphism is some of the projectives. And now when I don't have any more algebra, I look at the subcategory of projective factors, right? So this is just going from finite to infinite by using factors, and then using your method, replace this subcategory. So this is subcategory of the harms of the projective, replaced by F. So and FK, which now cannot be treated as endomorphism algebra, can be viewed as the category FK by identifying these endomorphisms with all the homomorphisms, category of all the homomorphisms, but then category of all the homomorphisms using your lambda is equivalent to that. Okay. And then do the same thing with CK. And F, that's what I saw people say, FK over CK. Now this, you can use projectives, but now with CK. Right, so I would just go use CK of XI. So it's exactly the same. And then again, use your lambda and you get to CK. Okay. So then now this decomposition of the projective factor over CK as the sum of a projective factor over FK and injective factor over FK, that carries all through so that we get the projective factor over CK, which identifies with CK, is equal to the sum of the projective factor over FK and injective factor over FK, which is the same projective structure over that. Okay. So this is just by using this full identification, using this Yoneda and this fact applied to the subcategory of factor, instead of taking the sum, you just take the entire subcategory of factors. So you are essentially looking, so everything is, oh yeah, there is another question that you asked me. So we are essentially looking at finitely presented factors on C on finitely presented factors. And then you ask, so there is also this here, right? So this number here was supposed to be the global dimension of the lambda, right? Global dimension of lambda to use. Okay. So then Milan asked me, what do I mean by global dimension of a subcategory, right? But for that, again, I just want to kind of like make it short.
Mhm.
It's kind of really hard. And you say global dimension of R.
Mhm.
What you mean is supreme of projective dimensions of n, where n is in module, in mod bottom, right?
Yes.
Okay, so now when I have category Fk, I view it as projectives, just as it is projectives. And then to say global dimension of Fk, I mean global dimension of projectives. And global dimension of projectives is supremum of the projective dimensions of the modules. So that means that this here, global dimension of Fk is supremum of projective dimension of finitely presented parameters. That- That's it. And
What is the generality in which this last theorem holds? You mentioned that this now is way beyond thinking quivers.
Hmm?
What is the generality of the last theorem?
well, for now, we only looked at the derived no, there is also another part which is more general. Okay, so so the way I stated it, this is for this CK K cluster categories in that sense, which starts with the quiver, which with the hereditary algebras. Okay,
So
but then then there is another part which is also for higher cluster categories that I don't know well enough. Okay?
Mm.
Higher cluster categories that Alperman and somebody, now I don't remember names, I'm sorry,
Mm.
but there's other higher cluster categories, and then in these higher cluster categories, you can pick proper things and then do kind of very similarly to that. But I'm sorry, I really don't. But there is another version of higher cluster categories, not amyl cluster category, but higher cluster categories. Okay.
Mhm. Thank you. Let's go down. Any questions?
I just want to have both boards written up. Okay, my both words.
So I didn't exactly understand the appearance of the finitely presented functors or the fine envelope of your original category. So here you define the unit embedding of an additive category into the pride envelope. Those are the images. So then what is the role of the Fried envelope in the theorem? Where does like the finally presented functors that enters?
Well, finitely presented functors are modules,
Mm-hmm.
right?
Mm-hmm. Yes.
So
No
it's
modules.
just like,
Mhm.
right, when you talk about global, that's why I wrote this here, when you talk about global dimension, right,
Yes.
then you look at the projective dimension of
Yes.
modules. And finitely presented functors, this finitely presented functors actually quite a number of people nowadays.
Yeah.
So many people I guess I'm used to writing FP,
Yes.
F, or whatever
Yes,
is
yeah,
the
yeah.
category F.
Yeah.
And many people now write it as small
Yeah.
F.
The small module category. The people usually call that the small module category,
People, it's small.
or the Fried envelope of FK.
Yeah, it's called, small module category, but it is, I mean, you have to understand that there are factors.
Of course, of course.
Yeah.
Yes.
So, but I guess because I'm kind of, worked with
Yeah.
from Auslander, I was kind of used to that, and so usually, but it's.
Yeah.
It's a very.
Mhm. And you embed FK into this gadget via the UNED embedding, and
Yeah.
this is an abelian category. So what's the role of that abelian category so in the theorem somehow you don't really work with this abelian category, or it's implicit
You mean-
somehow. In the theorem, it enters in the definition of
You mean FK?
FK is embedded in the small module category via
Yeah,
UNEDA.
So you look at everything in the category of finite exactly,
Mhm.
right?
Mhm. Mhm.
So, I don't understand what is the role of what, and then in finitely presented functions, you compute the projective resolutions.
Yeah, but what's, okay, well, I was kind of wondering what's the role of this in the theorem, because
The role of what?
of the,
Because it,
of the small module category, like, of, in,
of this, you mean this part?
yeah, what is the role of this in the theorem actually? Because in the theorem, you describe that C and F are equivalent to the corresponding, to their images in these categories.
Yeah, okay, so this part here
Mhm.
says how you relate the category of
Mhm.
finitely presented functors on Fk
Mhm.
and finitely presented functors on Ck.
Okay. Mhm.
So this is actually the crucial, because, okay, so for any finitely presented functors, the first thing you want to understand what are projective functors, right?
Mhm.
So this says that projective functors in here
Mhm.
are projective functors here, which is this little short one here,
Mhm.
and expanded by the injective functor also over the
Okay.
smaller category. That's what you meant, small.
This,
Okay.
yes.
Yeah. So what would happen is, you see, if it is, if you think about cluster category, okay, and you're going to fold it,
Mhm. Mhm.
then, let me use a different color. And then you want to look at the projective functors over the cluster category. Okay. So if I take a module here, now to find projective functor over the cluster category, I want to look at all projectives which are there, all modules which matter. Okay, so I look this, okay, I get some things which map to this, right? And this green part here corresponds to the this part. Okay, so this is a little projective over Fk. Okay? But then, you see, it has to be expanded by something else. And what it is expanded by is when you fold this, then this part is going to get there and it will be expanded by something like this. So this will be injective in, and Fk. Fk. This part here going up to here, and this will be projective And okay. Okay, but then if you close it and you know, the cluster object, the cluster category will look sort of like that, right? So then this first part is this, but then the second part is in the back here. And that is this projective, that is this decomposition projected into two smaller modules. You see, it's not that both are projective. One is projective, one is injective, but they are in the smaller. Is that what you asked?
Yeah, yeah.
Okay, okay. No, I wasn't sure. I mean, I was talking, but then I wasn't sure whether I'm answering your question.
Any other questions? Let's thank Gordana for this wonderful series of lectures.
Thank you for giving me a chance to talk. I actually really enjoyed it. I must admit, I enjoyed it, even though I'm sick, but I think I like all of this.